Okay, so now that we've got a basic handle on what a signal flow graph is, let's talk about some of the rules for breaking them down and manipulating them. So your book gives 4 basic rules on how to simplify and manipulate a signal flow graph. So we have rule number 1, and it is called the series rule. And all it basically says is you imagine one node feeding into another node, which feeds into yet another node. So I'd call this maybe, let's say S21. We'll just follow the notation in your book here. And then it calls this S22 over here. And this would be V1, V2, V3. What I can do is just replace this with a single branch like that, where this is V1, V3 again, and it's a single branch, and I just multiply these two guys together, S21, S22. All right, so that's the series rule. Like it's similar to like if you add 2 resistors in series, they sum. In this case, 2 branches in series, their coefficients multiply. So let's do rule number 2. This is called the parallel rule. And again, this is all in the book if you ever need to review it. So you can just start with, here's a node here, V1, and then here's another node, V2. And instead of one branch feeding it, suppose I have 2 branches just coming together for some reason. Okay? Or alternatively, you can imagine something like, here's a node feeding here, and here's a node also feeding into it. And they're very similar in this sense. But the idea is, this is, say, I'll call this SA for S branch A and SB. So what these do, so I'll call this SA again, SB. So these are actually slightly different. In this case, I have 1 voltage kind of taking 2 paths. This is 2 voltage adding together in a sense. So we'll kind of hold off on that. But this guy here, you just add them together. You would just say a single branch comes together and I get SA plus SB. In a situation like this, if I had, say, VA, VB, and VC, you would essentially have VC is equal to VA times SA plus VB times SB. Okay. So I don't think the book quite makes that explicitly clear, but if you see I have 2 in parallel, it's just 2 signals and they add together. And related to that is this notion if I have 2 nodes feeding together into one, you would add them together in this sense. Okay, so if I have series lining up, they are multiplied. When parallel, they add. Okay, so this would be V1, V2. So if it's a single node feeding into one, you just kind of lump them together into an addition. But more generally, you can say 2 branches feeding into the same node just represents a superposition of that voltage. So let's go to rule number 3. This is now the self-loop rule. Like that. So you could have, hypothetically, a situation that does this. So here are 2 nodes. One feeds in the other, and this one might just kind of create a little feedback onto itself. So here's a branch. So any branch that goes from a node back onto the same node, there's a special simplification. So V1, V2, and V3. This guy here is my S21, and your book calls this one here S32. I don't know why they just say S, A, B, and C or whatever. But this is the notation your book uses. This now simplifies into something more like the following. Here, so I have V1, V2, and then V3 again. And this guy here gets lumped into this one feeding here. So you see the 2 sort of feeding in will add on to each other. And what you get is S21 divided by 1 minus S22. Okay, so don't ask us to prove that. We're just going to take that as a rule, taking that for granted. And then, of course, this is still S32. So nothing over here has changed because this node was just feeding onto itself. So you notice that loop here can kind of lump back into this single branch. And then, of course, I could apply the series rule again up here if I wanted to simplify one more time. So why not? Let's just do that for fun. So if I had V1 feeding into V3 again, using this rule here, you would get S32, S21 divided by 1 minus S22, like so. But that's the self loop rule over here. If I have one node feeding in and then it feeds on itself, this is how they combine in, which we could, of course. So yeah, I don't know if the book really needed to include this, because I could have just done that, I suppose, but that's kind of how the book describes it. So that's kind of what we're following here. So rule number 4 is as follows. It's called the splitting rule. This one's a little tricky. Let's just draw this. So if you have one node coming in, and maybe it branches off like this. Okay, so this guy feeds out to here to 2 nodes. So I'm going to call this V1, V2. Of course, we're feeding in V3 and V4. So 1 in and 2 out. S21, and then it calls this S42 for some reason. And then S32. Oh, I guess, yeah, it's corresponding to the subscripts here. So that makes sense. Going from, so you see this is voltage 1 and 2. So it's the output, the voltage at 2 as a result from the voltage of 1. So that's kind of how we're denoting it here. So the splitting rule then says the following. You can break this little branch and connect it over here in accordance with a different, slightly different rule. And it'll look like this. So basically these two systems are equivalent. And you can imagine another node here. So this is V1, V2. This is now V2 prime, V4, and V3. And these come in like so. So you can see, like, if I'm branching down here, I can imagine as if it's coming from this node over here, and the flow of information down this line will be essentially the same. So it's S21 and S21 again. So those are the 4 decomposition rules for signal flow graphs. Let's see if I can squeeze them all in there. The series rule, parallel, self loop, and splitting rule. And what we're going to do next is derive the simplification, we're going to derive the equivalent network for error correction in a vector network analyzer. So remember when we did lab 2, we just kind of threw some equations at you that we use for the calibration, right? So what we're going to do now is use these rules to show where that calibration equation came from.